Hey, welcome to my YouTube video. Yeah, so this is my category theory, and I previously introduced some special category called group point. And in this video, I will introduce I think probably the most important one in the homological algebra, algebraic geometry, algebraic topology, Abelian category. And so this video will be very introduction, and I will give the basic definition of the Abelian category and also explain this terminology that I think I basically originally in my previous video, I already introduced like a kernel, co-kernel, and zero objects, and also I will explain what this sentence means. Monomorphism, epimorphisms, this I think already introduced. Okay, and yeah, there's a very interesting thing that okay, I will explain what you mean by kernel of the. There is a one definition of Abelian categories that like kernel, like the monomorphism is a kernel of a kernel and kernel of a kernel. Yeah. Okay, so let's start. And yeah, I don't know why it said to me some chemistry, but who cares? Okay. Yeah. So basically, I will introduce this one by one. So don't worry. Okay. So basically, you can just Google and find a lot of reference for Abelian category. So I think I don't give the example. I don't give the explicit reference, but tensor category is a good book. Okay, so yeah, you can go to find the tensor categories. There's a book, I think it's by E.G. and O. There's 4 people that this is their name. And their first chapter is Abelian category because Abelian category is like the starting point of the homological algebra. Okay, so let me just quickly start. So let's say the functor. So remember that we already introduced a category. So let's define a so-called functor. Suppose I have a functor from C to D, and I say this functor is an equivalence. So this definition I will use in the future. Okay, if there is a, let's say F inverse such that D to C is another functor. This is called quasi inverse such that F inverse F I is so isomorphism on C and FF inverse isomorphism on D. So this isomorphism need to use the ideal coordinate transformation. Okay, so this is the definition. So say that the two category are equivalence. Sorry, there's a when I say two category are equivalence, I'm saying that there is a functor from C to D such that this holds. Okay, and yeah, these are all. This is the new definition that I think I haven't mentioned. Okay, so now I can define a additive category. So additive category C satisfy the following. Okay, so now so first one is that so given any two objects, right? Let's say given x, y, which would be the object of the C, use C, and the home set C, x, y are is an abelian group. Right, so in general, this home set is just a set, right? Need not to be the abelian group. So there's an additional structure that make it to abelian group, and I usually use addition as the group operations. Or in the A2, there is a zero object. Okay, so the zero object means that is previously I defined is the so-called terminal, is the initial object plus the terminal object. So basically, zero means that there exists the unique map from any object to or unique morphism from any object to zero. And for each B, there's also a unique one, right? So in the abelian group, this zero object just identity group. Okay, 3, and byproduct exists. So basically, given any two A1 and A2 is objects, you can define A1 addition A2. Okay, so to be more precise, let's say maybe I use X and Y. Okay, let me just change the notation. So let's say given X1, X2 belongs to the object of the category, and you can find there exists Y, which denoted as the X1 direct sum X2, such that there exists like a P1 Y to X1, which is a projection, and a P2 Y to X2, and also the combination, right? You get X1 to Y, which is an injective, X2 to Y. So these are all obviously in the Abelian group. If you take the C to be Abelian category as the category of the Abelian groups, then this will be obviously, right? Because you just take two Abelian group and take the direct sum. So this will be the first coordinate, second coordinate, and these are all projections. But abstractly, we need to write it down, right? So satisfy the such that, let's say P1, I1. So P1, I1 will be identity on X1. And the P2, I2 will be identity on X2. And also more, like the I1, P1 and I2, B2 will be IDY. Okay, I mean, you can check for Abelian group. I think this is very simple. Okay, and this guy is called direct sum. Okay, so this is the direct sum. Okay. Okay, so this is additive category. Okay, and also let me just, there's another definition. So when I say the additive category C, so this is also people like to use additive. This is also a definition, a useful definition. Additive category C is K linear. By the way, K is a field, and usually use a complex number, right? So K linear, if basically your home set is not just a Abelian group, but a K vector space. If all X, Y belongs to the object of C, home of X and Y are K vectors, K vector space. Somehow like filming a YouTube video is not easy thing, especially talking about what I want to talk. Okay, so another definition. So if you have a functor from C to D, when I say this functor is additive, so it means that this functor preserve is byproduct, right? Sorry, not byproduct. Additive means that. Means that what? Means that if so, from a right hand side, right, you have a home, let's say X to Y, and right hand side you have a functor F map X, F map to Y. So these are all the Abelian groups, and for each X, Y, they are isomorphism. Okay, so this is called the additive functor. Okay, and very simple exercise. This is very simple. You can check for yourself. So by the previous definition, you can check that if you compute fx direct sum f of y, well, isomorphic in the D category, in this D tag category, will preserve the direct sum. Okay. Okay. By the way, this is this direct sum is like a bifunctor. Okay. So I will talk about bifunctor in the future. Okay. Also, let's quickly define Abelian category. Definition: Abelian category. So somehow like these mathematics, these kind of abstract mathematics, somehow like spread their different pieces in the literature, and none of them are and so not very difficult to read in the beginning. So somehow this is why I want to make a video to combine all of them. Okay, so so suppose let me just quickly define a kernel, right? So suppose let's say you start from C is an addictive category. Let's say you start from C is an addictive category, and then you consider two objects X to Y, and then there's a morphism F. And you can define a kernel, right? I think I defined kernel before. Let's say kernel F. So I'm not saying the kernel F exists, right? I just say that suppose if kernel exists, means that there's object K. I use larger K and a small K. With the morphism, I use a small K. Maybe I use kappa. Kappa from large K to X. And there's F, right? Such that the first one is F K. So F kappa, right? So any kappa mapped anything go to X map to F is 0, right? This is the somehow like the usual definition of kernel, right? Usually when I say kernel, I will believe that I will think that kernel is some subset of X such that map to 0. I mean, if there is a 0 notion in Y, but now in the category, I cannot say X has the additional structure. So maybe this is the natural generalization that I put kernel as this kind of thing. And there is a universal property. Okay, so every time you see somebody tell you the universal property, that you are very happy to prove that this is unique. Okay. Such that if you have another K prime, or another kappa prime satisfy this property, then you will factor. Okay, such that this if Fk prime, let's say if Fk prime is 0, then you can factor through, right? So there is a factor from K prime, right? So there is a factor. So someone like K is the smallest one, right? So there is a factor. So there exists L, I think unique from K prime to K, such that this diagram commute. So I should say this. Okay. Kernel. Okay. Okay. So and obviously that kernel F. So in the category thing, kernel is not just a subset of X, but the object and the map. Okay. So kernel F is unique up to isomorphism. Okay, and you can also define a co-kernel. So in Abelian group, that the co-kernel is very easy. Suppose you have, let's say, A to B map and the homomorphism, and you can define a co-kernel just B modulo image phi. And if both are Abelian category, then the Abelian group, then B modulo image phi will still be Abelian. This is co-kernel. Okay, but in this abstract category, right, the co-kernel is something that's called C here. Band notation, right? But a small c, and such that Cf is 0, and also if there's another C prime, such that the C prime of F is 0, then there's a unique factor 1, right? So you can find a map here. Okay, so this is unique. So the same thing as a co-kernel. Okay, and you can also define an image. Okay. Okay, so let me just give a definition. So this is one definition. So Abelian category is very amazing that I up to now I didn't talk about any example. So Abelian category is an addictive category. It's an addictive category C, satisfied for every phi from X to Y. Any map there is a exact sequence. Okay, the problem is that I haven't defined exact sequence in the Abelian in the category, right? So I need to tell you the definition. So X, Y, phi, and you can break it into, like, say, X to I to Y to C to K, right? So this is a kernel, and this is a co-kernel, and this is an image. this guy is exact. So basically, given any phi, you should find a kernel and some image and some co-kernel such that. Let me just label it. So this is I use kappa, kappa I and J and C. Let me just pull it here. Okay, such that first one. So this is exact, right? So that means so Ji, right? So Ji is phi, right? This is the definition. And your this larger k, small k, will be the kernel of what? Kernel of phi, right? And your larger c, small c, will be your co-kernel of phi. So you will think this still be the abelian group. So if you use the group isomorphism theorem, and the fourth fact is that your I will be the co-kernel of K. Okay, and this IJ pair will be the kernel of C. Okay, and this is very tricky. This is very tricky idea. Okay, let me explain later. Okay. Okay, and this is called the canonical decomposition in the abelian category. Okay, and I is called the image. I use I and phi. Okay, so somehow like sometimes people are very lazy, so they will just use K and C. Okay, so by the way, the canonical decomposition is unique up to isomorphism. Okay, so only one example I want to show here. Sorry, not like 3 examples. The first example is abelian category, abelian groups. So each object is abelian groups. Morphism morphism are homomorphism. Or if you make a field K, you can use a K vector space, which the morphism are linear transformation, and you can also use the R module. Okay, are all abelian categories. And the proof, I should say just one line, just what? Group isomorphism theory. I think you only need one, the first group isomorphism theory, right? So for example, let's consider the abelian groups, right? Phi AB, then you can do the image, right? So you can do the image of phi, and the image of phi is a subset of B, right? So you can make this guy, and these are just A map to image phi, just map to phi, and what is the co-kernel? Just B modulo image phi, and what is this? This is the kernel, right? So just kernel phi. Okay, so and this map is just injective. Okay, so these are injective map. So I use kappa, and I think what? Sorry, I should say I and J, and all these are phi. Okay, so what I do such stupid thing. Oh, so I'm stupid. Yeah. So basically, let me just go back, right? So first, Ji equals to phi, right? This is stupid by the definition, and so this is kernel phi. You need to prove this, right? But in this case, the kernel phi this kernel phi just the subgroup of A, right? Because A are abelian group, and co-kernel is just the co-kernel. And let's check this one, right? So it says that this guy is a co-kernel of K. Read a little bit weird, right? So this guy is a co-kernel of the previous one. So this guy is a co-kernel. What it means, right? So in Abelian group, these guys is the put, just the image, right? So which says that the image is a co-kernel of this one. Okay. So what it means is that image is just the co-kernel of a modular kernel phi, right? So this is what? This is exactly the first group isomorphism. Right. So if you know the group first isomorphism theorem that you just prove so if you speak out the group for the first group isomorphism theorem, then you are just saying this. Okay. So this is what it says that this map is actually the co-kernel of the kernel, and this map, this ij is the kernel of the co-kernel. Okay, so this is co-kernel of kernel. This is the kernel of co-kernel. Right, so crazy. Okay, so and then you can check that this j, so this j in here is an injective map, right? So it's just the kernel of this, right? Because this is onto, right? The kernel of the quotient group will be this, right? So this guy is just the kernel of this. Okay. So in the Abelian group and the K vector space are modular, obviously Abelian category by the first group isomorphism theorem. So someone like this is a generalization of this guy. So that's why we define this. Okay, and yeah, I think this is okay. And let me just say something. So once you have Abelian category, then you can define a lot of things. Right, the first thing is the exact sequence, right? Because you can define sorry, if you have let's say a prime, and it's let me just erase something. Yeah, so in the Abelian category, you have a notion of the exact sequence, because let's say you have A1, A2, A3, let's say F1, F2. You have this morphism, then you can define exact sequence by just saying that image is the kernel. Image is the kernel. This is okay because in the category, I already have kernel, I already have image, and I'm okay to speak that where they are the same. Okay. And you can also, so you have the also short exact, long exact, and then you have the snake lemma, and like the short 5 lemma, 6 lemma, 7 lemma, that kind of things. Okay. And then not just that, and the things is, and you can also define. So basically, you can extend this into, you can bring all the homological algebra into this kind of thing. Okay, and let me just, and you can talking about like the idea of the left exact in the category, right? And in the Abelian category, because you already have exact. Right, so for example, if let's say from C to D, left exact means that suppose you have some exact sequence like this. If F is left exact, means that apply F still exact. Right, so if this guy is exact, and if this guy is exact, these are called left exact. And if you learn about the basic topology, and for example, you can take F to be Hom. Okay. I think you take something. I think maybe you take this. Yeah, should be left exact. Okay, and you can also define the right exact. And the famous example is the tensor. Okay, so tensor structure is a left right exact. For example, you have ABC. Let's say BC 0, and then you focus on this part, and then you can tensor. Let's say you tensor D. Then it will be this, and this guy may not be exact. Okay, so tensor is the right exact, and if you learn about the cohomology or the derived category, then you can try to make you can make this, you can try to save this left or right exact, and then you can define you will get something called a torsion group. and the higher X group or higher torsion group, which comes from this. Okay, and then you can also define the, since you have the homological algebra, so you can define the projective resolution, or like the injective resolution. Because now you're in the Abelian category, so everything turn out in the module that in the R module you can bring it, right? So let's say you can define of this and take a hum and then compute some group, and also you can also define a group cohomology. Yeah, I think this is what originally group cohomology comes from. Okay, so yeah. You can define, you can start, these were related to group cohomology of this. Maybe I will talk about group cohomology in the future. Okay, so the final idea that I want to introduce, I think it's a little bit important, is a simple object. Okay, so the simple object, let's say X is a simple object. In the C, in the category C, if 0 and X, 0 object and X are the only sub-object. Okay, so let me explain what sub-object means. I think I haven't introduced. Okay, yeah, I haven't introduced sub-object. Okay, so sub-object means that the sub-object of X means that there is a monomorphism map to X, right? So this is the sub-object. This M is some object in the category, and F is a monomorphism. Okay, and you can check for my previous video what the monomorphism mean. But basically, in a set, you just injective. In an Abelian group, just homomorphism but injective. Okay, so this is called sub-object. I think sub-object idea, this idea are very important. And okay, and this is the first. The second is that the semi-simple object. So X is called a semi-simple object if X is a direct sum of the simple objects. If X is a direct sum. So remember, we are in the Abelian category, so I'm very safe to say what is direct sum. So it's a direct sum of a simple object. So this semi-simple and the simple object idea are also common in the mathematics. For example, if you're talking about the representation of the finite group theory, and all the finite representation is a semi-simple, so it can it can be written as a direct sum of the irreducible representation, because and the irreducible representation are simple. Okay, and there's a short lemma which I will prove this in the group theory, sorry, group representation. But there's a abstract one. Suppose you are in the Abelian category, and there's a two simple objects, X and Y are simple. Okay, so the very famous example is that you think about the representation category, or sorry, X and Y are both two irreducible representation. Then Shor's lemma tell you that the only equivalence map between two are K, right? K linear, are K vector space, right? So I think the good example is that you think about the group representation. Okay, so the generalized Shor's lemma is that any non-zero morphism from X, Y are isomorphism. Okay, so this is the same as this. Okay, so just saying that this just saying that in particular, if y is not the same as x, then the Shor's lemma tell you that hum of xy will be 0. Okay, and also, and Hom of XX is a division algebra. So in the original group representation, that usually people say that the Hom of XX just the K vector space. If you are working on representation of field K. Okay, so this is the short lemma in the Abelian category. So it's somehow like the generalization. And there are many other things about Abelian category, but this is just an introduction. Yeah, so, but I think once we have the Abelian category, and one can define a coalgebra and other kind of things, and one can start from here and go to the monadial category and the braiding fusion category and the rigid category. So there are a lot of things, and the triangular category, derived category. So this is a very interesting category combination. Yeah, so hope you guys like this channel. Subscribe.